We're going to see Ampere's law in an electromagnetic wave and defining that we will encounter here together with the result with Faraday's law for the electromagnetic wave would lead to the answer of the speed of light. So first here we have y, here x, the positive x direction. This would be the negative y direction. This is the negative x direction, and like this is the positive c direction. So let's say that the propagation of the wave is in this direction, in the x direction. So we have here the electric field, like this. The magnetic field would be in the x and c plane, so it would be something like this. So this is the electric field, and this is the magnetic field. Like this. So the propagation is in the x direction. Let's say that this is a picture at the time t equals 0. We have that Ampere's law is that the closed integral of the magnetic field dot dl in a closed surface. So it's a closed loop with a attached surface. The surface could be open or not. This would be equal to the mu naught times magnetic permeability K sub n times the current penetrating the attached surface plus the dielectric constant times epsilon naught times the change of the electric flux in dt. In this case, because we are in vacuum, there is no penetrating current, so this is 0, and the magnetic permeability and the electric constant is 1. So this is 1, this is 1, so we just have that the integral, the closed loop integral of v dot dl is equal to mu naught epsilon naught times the change in flux of the electric field in dt. So we need to calculate what is first the electric flux and then take its time derivative, and next the this closed integral of v dot dl. So first the electric flux. So for the electric flux we have the Gauss law for electricity, that is the closed surface of the electric field dot dA. This A vector is the vector which magnitude is the length or the magnitude of the area, and the direction is perpendicular to the surface of the area that we're going to take. So the electric field will be changing. Here we have some electric field, here we have another and another. So we will take the integral from here to here. We will take a surface. This surface, this surface with length L and width dc. So the area of our surface is dc or L dc, and the electric field at this point we have, in all this part we have the electric field equals, let's say, this E max or E sub 0 in all this time, but we need to integrate this here from from here to here we don't want only in this C, we want in all this part, let's say from C equals 0 to lambda over 4, because this is a quarter of the wavelength. So the electric field, in previous video we saw that the equation for electric field in a electromagnetic wave could be cosine or sine. In this case, cosine of this k is the wave number of the wave times the propagation. In this case, could be c or could be x, times plus or minus depending on the propagation, the omega times t. So the velocity is always, in this case, is velocity, that is c, that is omega divided by k, and we know that 2 pi over k is equal to the wavelength. Alright, so here the electric field would be the integral from 0 to L over 4 of electric field is cosine k c minus omega t, and the area is L dc. So now we will take the derivative of the electric flux. So L is a constant, and we can take the derivative of what is inside and then take the derivative. So in some part we will have the integral from 0 to lambda over 4 dc. The derivative of this part is the derivative of cosine is negative sine of whatever we have in here. So this would be negative sine k c minus omega t times the derivative now of what is inside, that is just the derivative of this, that is negative omega. So this would be positive, and here I have the omega, and then here the dc. So now the integral of this, we know that at time 0 is when this is happening, so we can put this, all this becomes 0, and we just have to evaluate this part. So we have that omega L times the integral of sine of this stuff is cosine of the stuff divided by this, that is divided by k. Because here we are taking the integral with respect to the c, not with respect to t. And this will go from 0 to lambda over 4. So we have the derivative of the electric flux in dt is equal to this would be omega over k. This is c, so it's c, the speed of light, times the length, and this would be cosine of k lambda k lambda over 4 minus cosine of 0, which is 1. Here the k is 2 pi over lambda, so here would be 2 pi over lambda times lambda over 4. This is pi over 2, and so we have the cosine of this is just 0, and we just have that the electric field in the derivative of the electric field in dt is the speed of light times L, or I forgot to put the, here I forgot to say the electric field is equal to the electric field not times cosine this, so to put it here. So we have this first part. So then we will multiply this times mu naught and epsilon naught, and then we want to find the closed loop of B dot dl. So this is again our surface, this. So in, let's say, 1, 2, 3, 4. So the magnetic field is in this direction and L is in this direction. So the first part of this B dot dl, here L and B are parallel, are perpendicular. So parallel. So there are 2 points in which L and the B or magnetic field are perpendicular. That is, in this part L, and in this part L is perpendicular to B. So from 1 to 2 we have that B dot dl is equal to 0, and also from 3 to 4 B dot dl is equal to 0. Here from 2 to 3 the magnetic field is 0. So yes, it would be parallel to L, but in this case it is 0. So again B dot dl is 0, and so the only contribution to the closed loop of B dot dl is this part is 4 to 1. That would be this maximum magnetic field. I should have put this here. The maximum magnetic field B dot dl, or B max. And so now we have that B BL is equal to mu naught epsilon naught C L divided by epsilon times the this electric field at this point, the maximum electric field. So we can cancel the L's, and that is, we have B is equal to mu naught E naught C times the electric field. So this is what we got from Ampere's law for an electromagnetic wave, and in the next video we will continue with Faraday's law in an electromagnetic wave to see why C, the speed of light, is equal to 1 over the square root of epsilon naught and mu naught.